Okay, so just before we get going, a little bit of background on flow, because I don't think many of you have attended this session before, so it's relatively new to everybody. Why did we actually produce flow? Well, without being getting into too much of a long-winded explanation, really it was based on feedback from industry, and we had a number of customers and potential customers out there that essentially said, yeah, we'd love a drainage design program, but essentially what's out there is one, a bit limited, actually. There's not too much around. What is around isn't necessarily suited to the commercial market or the UK market, and most of them actually are quite expensive. So that's what really inspired us to develop Flow. We wanted to produce something that was easy to use, was accessible to people, and provided we get away from this idea of modules and you have to buy this module, that module, have everything in one package, so end-to-end design. And that we thought would make the whole process faster. So, that's what we've achieved, I think. We've also looked at trying to make it integrate with other industry standards out there. So we do support industry standards for working in a mixed environment, or where you're maybe working with colleagues using other programs. You can actually work with them and exchange data. And we've integrated it with PDS fairly obviously. And via that route, obviously you've got the integration with CAD as well. So really that was as much as I was going to say in terms of the background, just to give you a little feel for why we've done what we've done. And we'll crack on now into actually looking at some software. I'll pop up at the end again this slide, but just in case you wanted to make a note, we've got trial copies available, so you can actually go and download a trial version of Flow. Any questions that you don't have a chance to ask during this session, email me please. So into PDS then, interface that those of you that use PDS will be familiar with. I've put together here a fairly simple layout, just not too much in it, just to give the principle here really. So we've got a storm and fail drainage network in place here. I've actually gone through and loaded this as well, so I've actually put some catchment areas in here. I've loaded the fail system with a number of dwellings and so on, just so that you're not having to sit through the whole process again. So I've done the layout, I've done the loading. The next step is to export. Now obviously we've got a few things on the list. Some people will be used to exporting to micro drainage, where you can still do that. We've got another one on the list now though, which is Flow. So if I just hit this one here, I want to take the design that I've got on screen, or the layout that I've got on screen, to Flow. Because Flow's on my machine, it will fire up automatically. And if I say OK there, it wants a name. So if I just say, I'm just going to call this DR1, I'll replace the one that's there. And you can see it's writing out the data for the pipes, i.e. the loading and the lengths and so on. Activating Flow, because I've got Flow on my machine and I said fire it up automatically, and I'm now in Flow. There are some key bits of information that the software wants to start off with. Obviously it's going to vary from site to site, some of this information. So essentially what I'm going to do is just enter, say, a 2-year return. I'm going to put in an M560 and R, and time of entry 5 minutes. Okay, that's all I need. So basically you can see I've got the starts of a long section down here. If I go in here and say design with capacity and cover, yeah, I've got 1.2 cover identified in here. You'll see this update automatically to now take into account the loading that I've got in here. So I can basically directly optimize the system to 1.2 cover. I could then go in and I could start looking at links, and I could look at nodes. Nodes are the manholes, links are obviously the pipes, and all of this information has been fed in terms of length and so on from PDS. I'm going to hand over to David now. I just wanted to cover that bit just so that you can see how easy it is to take a layout from PDS directly into Flow and start work. I'm going to hand over to David, who's going to run through in a bit more detail what Flow is all about, and then we'll come back at the end for a Q&A session. So I'm just going to hand over to David. I'll make him the presenter. And over to you, Dave.
Thank you, Barry. Hello, everybody. Hopefully you can see my screen. Today we are going to be doing a small storm network design. We will be connecting to an existing system, which means we've got a known invert level at the outfall, and we'll also be constrained by a maximum allowable discharge of 50 litres per second from our new development. And of course, no flooding for the 30-year return period. Now, the Flow workspace is organised into 3 panels. So top left, I've got the design elements tree that give us a list of all of the pages of data and the results that are associated with our design. To the right of that, we've got the current page of data that we've got selected, and at the bottom, I've got a graphics panel, so at the moment showing a long section. My design starts with the design settings. So today we're going to be using flood studies report rainfall, but we could design using flood estimation handbook as well if we want to, or we can specify our own IDF table so that we can use the program anywhere in the world. I'm designing for a 1-year return period. We've got the ability to specify an additional flow if we want to, so if we want to design spare capacity into the network, we can do. And then I've got my values from the flood studies report maps. The other things that are worth noting from the design settings is we're designing to 1 metre per second minimum velocity, which is the recommended self-cleansing velocity for a storm network, and we're working to a preferred cover depth of 1.2 metres. Our network is divided into nodes and links. And we've got some of the data already in the program. This has been entered through the spreadsheets in this instance rather than coming from PDS. So I've popped the data in for the nodes, and what I've done is I've specified a unique name for each node. I've given it its impermeable area, and I've specified a cover level for each one. These values are shown in a black text to indicate that they've been specified by me. We've also got some values in blue. These are the ones that have been calculated by the software. Now, the spreadsheets use a traffic light system to give us some immediate feedback on the validity and the suitability of the data as we put it in. So the green traffic light means everything is good. These nodes can be designed. We also have an amber traffic light, which is for an advisory. Now, these are things that may be right, but they're something that you might want to go and review, have a look at. So in this instance, nodes B1 and B2 are showing in amber, and that's because these nodes are currently not referenced by a link. These are going to form a branch line that we're going to put in the minute, so that's not a problem. And if we put some data in that's invalid, then it'll be highlighted in red to say there's a problem, and that's something that we have to go and fix. So if I look at the links, again, you can see some of the data has already been entered. In this case, these are the pipes that form our main line. I've specified the connectivity information, so the upstream and the downstream node, and I've specified a length. Everything else has been calculated by Flow, including the name for the link. Now, unlike the nodes, we don't have to specify the name for a link. We can do if we want to. So if we want to put something in that identifies that in the context of our job, we can do, but we don't have to specify a name if we don't want to. If we don't put a name in, what Flow will do is use industry standard pipe numbers. So if you're used to seeing your pipes numbered in this way, this is something you don't need to learn. You don't have to think about. which pipe should be which number. The software will do all of that for you. Now, as well as that, the spreadsheets are completely open as to the order that we put the data in. So in this case, I've specified the main line first, and now we're going to put the branch line in. Because that's the way I like to work. If you want to do things in the order so that you're always specifying pipes that contribute at the upstream end before you move downstream, you can do that. And if you want to start at the outfall and work backwards, you can do that as well. So there's no limitation on the order that you put the information in, and likewise there's no limitation on whereabouts in the spreadsheet you go. So we can put the rows anywhere we like, and then there's the ability later on to insert rows, delete rows, or move rows if we want to. So I'm going to start by popping in my branch line. So I'm going to say I've got a link going from B1 to B2. If I come off the row, what you'll see is that we immediately get the validation error, our red traffic light, because I haven't specified a length. Now, if our nodes were coordinated, Flow will calculate the link lengths for us. If we don't have a coordinate specified, then we've also got to specify the length. So if I can go back, type a length in to correct that, come off the row, and our pipe 2 is designed for us. Now, what we can see, if I scroll across in the table, is we've got an upstream invert level has been specified by the software, and that's been done to give us 1.2 meters cover depth as requested. The fall has been calculated by the software to be just above our minimum velocity that we've asked for, and we've got a 150 mil diameter, which is the smallest diameter from the pipe sizes that has sufficient capacity to take the flow. Now, we don't have to use those values if we don't want to. We're free to go and overrule any of them. So I can go back to full, type in a new value, come off the row, and the pipe is updated to reflect the fall of 0.1 that I've put in. Now, whilst that's allowed, what the software does say is it gives us this warning that our velocity is now falling below the self-cleansing velocity that we've specified, so that pipe 2 now has an amber advisory. So we can break the rules if we want to, but the software will tell us, well, we've done that. Likewise, I can go and increase the fall, and at this point, that's fine. Our pipe is flowing a lot faster, but there's no reason stopping us doing that if that's what we want. So I'm just going to put that back to software calculated, and then I'm going to put in the second length of our run that's going to bring it back into the main line. So again, I just specify the upstream, downstream nodes and the length, come off the row, and that's now hooked back into the main line. Everything is calculated for us, and we can see the end result on the long section below. Now, I can control the number of pipes that are displayed on the long section by using the plus and minus buttons. I can change how many pipes are drawn, and as I move through the spreadsheet, the long section will update to follow my position. And if I want to hold a particular view, I can pin it where it is, and then as I move, the long section stays put. Let's just unpin that and get back to looking at all of it. The shaded blue area in the pipes is our proportional depth of water, so this is what we're actually designing to. And the yellow shaded area represents those pipes where we haven't managed to get our 1.2 meters cover all the way along the length yet. The reason for this is at the moment, Flow is designing capacity only, so it's setting the pipe diameter and the fall to give us sufficient capacity and self-cleansing velocity, but it's not considering the cover level. To do that, I can change the design mode to design capacity and cover, and then the falls are increased where necessary to make sure that we get our 1.2 meters all the way along the length of the pipe, and we can see that now in the results, and the yellow shading has disappeared on the long section. Now, I said at the beginning that we were connecting into an existing system, and that would mean we would have to meet a known outfall level. In this case, the level we've got to reach is 99.1 meters, and we're slightly below that, 103 mil too low. This is the kind of thing that at the end of the sort of design or model build phase can be quite onerous. It can be a little bit fiddly to go back and just change those levels slightly. Now we could just go and lift the entire run, but that would break our 1.2 meter cover across the whole network. And if we go and manipulate pipes further down, of course, we risk not getting our required velocity. Now, Flow can take all of the hard work out of the process for you. I just put in the inlet level I'm looking to achieve, come off the row, and now we can see we were looking for 99.1. We've got 99.1. This has been achieved by flattening 1.002, which means the 2 pipes following it are now a little bit low on cover depth, but we've done that. We have still managed to maintain self-cleansing velocity all the way down through the network. So in most cases, that's the best solution we could hope for. Now, in this example, we're just working with standard circular sections, but Flow is able to calculate and design pretty much any section that can act as a flow carrier that can carry flow from point A to point B. Now, whether that's double or triple pipes, it could be box culverts, it could be a ditch, it could be a swale. This example is only looking at the circular pipe case, but as I say, we can model all of the other flow carriers as well. So with our network model now all in, our model build is complete. We've done our design. We're ready to go and analyze. So if I look at simulation settings, we can see that I've got the same rainfall information as I was using for design. We're going to be analyzing both summer and winter storms. We're going to run the analysis for the storm duration plus an additional 4 hours. This makes sure that our network starts to drain down, that we've captured the peak. We have seen our maximum flow rates and maximum storage requirements. We're going to be running storm durations from 15 minutes to a day. We could extend that all the way up to 7 days if we wanted to. And Flow has the ability to run multiple sets or multiple return periods in a single analysis if we need to, with or without climate change. So if we're interested in running 130 and 100 or 100 plus 30% climate change, we can do that. We can set all of that up in a single run. Today I'm just going to look at the 30-year case. So with my simulation settings ready to go, all I need to do is click Analyze. Flow will go away and perform dynamic wave routing analysis, and once it's ready, it presents us with the results. Now, from all of those storms, it's automatically gone away and calculated the critical duration for us, which in this case is the 15-minute winter. So this is the storm that produces the highest water level at each of the nodes. The results table shows us what our peak water level is, as well as information like the peak inflow. We can see the peak outflow, the velocities that have been achieved, and so on. The good news in this case is we have no flooding. We've got some surcharging in the network, but no flooding yet. Flood volume is 0. And as well as the critical, I can go and have a look at each of the individual storms if I want to. I can just run down through the list. And if rather than seeing a summary of the results, I want to see a full set of routing tables, I can do that, and then I can see the values minute by minute through the analysis. And if I scroll down through the table, I can actually see the water level animate on the long section. Now, as well as seeing that data in tabular form, I can graph it. So if I click on graph, I can go and get a graph of level, and as I run my mouse over it, it'll tell me the exact values, so I can see graphically where the peak is and what it is. And as I click on different columns, you can see each of the data sets can be graphed so that we can look at any of them if we want to, and again, go and query them just by running the mouse over. So really easy to get a really good understanding of what's going on in the results. So if we go back to our default view, so I said the good news is we have no flooding. Unfortunately, we can see that we have a discharge of 170 litres per second through the last pipe in the network, which is over 3 times our 50 litres per second that we're allowed. So what we need to do is introduce a flow control just to limit our flow offsite. What we're going to do is we're going to pop a control in down here on node 5. So come across back to the tree, select flow controls. I'm going on node 5, and you can see from the drop-down list we've got a number of controls listed. So orifice, weir, gate are all self-explanatory. We've also got 2 performance curve options, depth flow and head flow. Depth flow is suitable for modelling a pump. It's going to ignore the downstream water conditions. The flow rate will be determined purely by the depth of water at the control location, whereas head flow will consider the head loss across the control. It's looking both upstream and downstream, and that makes it suitable for modelling pretty much everything else. So I'm going to go head flow. Any of the controls can be made a non-return valve by specifying them as having them as a flap. We can make our control either online or offline. So online controls continuation flow. This is what we're doing in this case. Or I can make it offline so it acts as an overflow and takes water away from our network. So this one is online. If we mark a control as replacing the downstream link, what that means is that we consider the pipe not to be hydraulically significant. So our flow control acts as a throttle. We're going to analyse just that, ignore the pipe. This can help to stabilise the analysis or make the analysis run a little bit faster. If we untick the box, then we will analyse the flow control and the pipe in combination. And if you are ever in 2 minds as to which one is the right one, untick the box and go for both. In this case, I know my 50 litres per second is way below the capacity of the pipe, so I'm going to leave it ticked. I'm not going to specify an invert level for my control. By doing so, the control sits in the base of the manhole. It will assume to be at the invert of the manhole. The benefit for doing this is if we subsequently have to go back and alter any of the upstream network, in that the control will move with the base of the manhole. So if all of the invert levels change, even by a little bit, the control will move with them, and that just makes it much easier to go and refine our design without having to come back and re-specify a bunch of values. So I'm now ready to put in my head flow curve. At this point, what you'd want to do is go and approach the manufacturer of your favorite vortex valve. They are able to give you a performance curve that you can put into the software. If that's HydroBrake, they've got an online tool that can calculate that performance curve for you, and again you can copy and paste it into the table. So nice and easy. I'm going to cheat a little bit in this instance in that I'm going to assume linear performance from my control. This is a reasonably good sort of estimate if you don't have information to hand about the control you're using. So I'm going to say at 1 metre deep, I'd like a flow of 50 litres per second, so we can see the flow regime I'm going to get. And if I come off the row, I get a green traffic light to say my data is good, and down here we can see my control sitting on node 5. So the graphic makes it really easy to see that we've specified it on the correct node, and it's also got the correct level, and that just saves time in us running around refining a design when we've got our control in the wrong place. So with that there, I can run the analysis again. Okay, so we can now see that our outflow is down to the 50 litres per second we're allowed, but not unsurprisingly, we've now got flooding. And our flooding is about 47 cubic meters of flooding, so what we're going to have to do is introduce storage to solve that. That storage can be either as upsized pipes. We could go and introduce storage along these lengths, for example, or we could put storage in at this location, which is what I'm going to do. I'm going to pop in an online storage structure on node 5. Now, I always work to a first guess for storage of being double the flooded volume. And I'm often asked why I don't just use the flooded volume. Well, the reason for that is that when we put the storage in, we'll lower the water level, which of course steepens the hydraulic gradient along this pipe, which means we deliver more volume to node 5. So I always think if we go double the flooded volume, that's a good first guess, and we can refine from there. So let's do that. I select storage again. This is going to be online storage on node 5. And we've got a bunch of options for our structure type, sort of generic depth area table that we can use for a pond or a tank. And we've also got some specific structure types for some of the infiltration structures that we use these days, or an option for link infiltration. And this would enable us to assign the infiltration variables that would go with something like a swale that's already been modeled as part of our network. In this case, I'm just going to go for a tank, so I can take the depth area case. As I say, because this is just a normal tank, I don't need to specify my infiltration values. However, if your site is suitable for using infiltration, you go out, you can do the site test from BRE365, put the values in, and then the software will analyze the effects of infiltration as well. And it's all based around UK specification. Again, I'm not going to specify an invert level. I'm going to get my storage structure to track the manhole, and I'm just going to say at the base, 0 meters deep, I want 94 square meters, none of it infiltrates. We'll just assume straight sides for now, so that will give me my 94 meter cubed of storage at 1 meter deep. Come off the row, I get a green traffic light, I get a brown halo on the manhole just to tell me that I've got additional storage present, and I'm good to go and run the analysis. And then what we see is that we're down to 50 litres per second. We've got no flooding, and we can see we're actually using slightly more than 94. I'm using 99 cubic meters of storage, and that's because we've gone a little bit over the meter deep. So at this point, I could go back and upsize that structure if I wanted to. From a sort of first pass as a prototype or an optioneering approach, this design is plenty good enough. Of course, for a real job, we would go back, we would put the proper performance curve in for the flow control. We would then go and decide whether we're using a tank or a pond, maybe put the pond profile in for the storage structure, and just prove that it works for exactly the values we're going to use to finish with. But for now, I think this is plenty good enough. So the only other thing you'll want to do then when you're finished is you want to submit your results or get your results out of the software. To do that, I go and click the Design Report button, give it a file name. So yes, I'd like to open the report. We can have a quick look. So what we're doing is we're writing out each of the pages of data into an Excel file. You can have a look. I can see all of the data I've put in. I can scroll across. We've got all of our results in there as well. And obviously that's now ready. You can print that if you want to. You can copy and paste it into your own reports, or it can just be emailed onto the approving authority. So I think that's just about the end of my demo. So back to you, Barry.
Thanks, David. Well, I'll just take back control. So I'm just going to finish this off by just having a quick look at what happens with the flow data once you've done the design. So if you remember before, I'd actually analysed a system in flow. What I can do now is back in PDS, as soon as I go to do something like say annotate a layout, you'll notice that it's all updating. So it's reading the pipe network in that I took out and analysed earlier, which allows me to then carry on and do whatever annotation that I want to in PDS, for the, literally annotating the layout, popping this down in here, adding the pipe work onto the road long section boxes, manhole schedules, clash checks, etc. So really we've completed the circle. We've done the layout in PDS, we've exported to flow, we've looked at the design in flow, brought it back for all of the annotation. That's really as far as we were going to go with software today. We wanted to leave a bit of time for questions and answers. I will just pop up on screen though at the moment here. If you want to trial a copy, download a copy and try it, you've got the link in here. Please do feel free to go away and have a play with the software. Best way of trying it and seeing how you get on with it. And that's where we're going to stop the actual session.